Section 3.4, we're going to talk about concavity. Have you heard you've probably heard the word concave before. Where have you heard it before used? Can you think of where it was that you've identified that phrase or that word before? And what it was talking about? Anybody can think of anything? Yeah, you usually see it in geometry when you're talking about something being concave versus convex. Like we talk about how a spoon opens and it being concave or convex depending on which side of the spoon you're looking at or something like that. Algebra is actually the one that's most relevant to this topic. Do you remember where you heard it talked about in algebra, Hannah? No? It's okay. You usually hear it presented about the same time you're talking about parabolas. Parabolas that open upward are concave up, and a parabola that opens downward is concave down. So at least when you're talking about parabolas, you kind of get this sort of a word picture about the idea being that something that's concave up holds water. And that's fine as long as it has that parabola shape. But there's actually items that are also concave up that don't quite hold water. So we're going to actually talk a little bit more about how concavity comes into play. And we're going to have another test called the second derivative test. We did the first derivative test last time. And the second derivative test that tells us some information about concavity. So the first thing that we're going to talk about in terms of concavity is how we decide if something is concave up or concave down. So this idea of holding water is obviously not very mathematical, right? It's a word picture that's great to think about, but it actually doesn't even work for all the pictures that we would want to do. So a graph is actually going to be concave up if the derivative is increasing. And it's going to be concave down if the derivative is decreasing. Now you have to be really careful. We didn't say the function is increasing or the function is decreasing. It's the derivative. So let me draw two pictures of graphs that are both increasing, but they increase in a different way. So this is one graph, and then this is the other graph. Both of those graphs increase, correct? Yeah, they're both increasing graphs, but they're acting very differently. One graph, the first one, is if you try to draw tangent lines, those slopes in there, its slope is actually leveling off as you get to the top. It's like you're approaching the top of the hill, right? And it's flattening out somehow, or at least it appears to nearly be flattening out. At the very least, you can say that the slope is not as steep at the top as it is at the side where it started. Okay, so this graph over here is the second one. This is called concave down. Because the slopes, that is the derivative, is decreasing. You get a flatter graph as you move from left to right in this particular portion of the graph anyway. The second graph does exactly the opposite. It starts out pretty flat, right? I mean, like I wouldn't mind running on that little bottom piece. I'd have a really difficult time running if it got to this vertical side over here, right? I mean, it gets really steep. So when a graph starts out really flat and it gets really steep, that's actually a concave up graph. And if you sort of compare these images to the parabolas that we sort of talked about having seen in algebra, can you see the image there too? They kind of almost look like half of a parabola, like an incomplete picture. But the first graph is in fact looking like if I completed the picture, it would be opening downward like a parabola. And the second graph, if I completed the picture, looks like it's opening upward like a concave up parabola. Okay, so that's all well and good. The question then would be how we decide when a graph is increasing or decreasing. So you think with me for a moment. We just did a section on it. How did we decide in 3.3 when we had a graph that was increasing or decreasing? What?
When there's a negative for the first number.
I know what you're talking about. You're thinking about when we were talking about looking at the cube root graph specifically, but I don't want to look just at the cube root graph. I want to talk about any graph in general. We talked about finding a derivative, right? We talked about finding the slope of the graph. So if we wanted to know when a graph was increasing, well, we looked at when the derivative was positive or negative or zero. That's when we talked about whether it was increasing or decreasing or flat, right? It's when the positive, negative, or zero. So whenever a graph is actually increasing, its derivative is positive, right? And when a graph is decreasing, its derivative is negative. So we can actually talk about whenever this derivative graph is increasing by looking at its derivative. So what is the derivative of the derivative? That's the second derivative. So we're going to encounter the second derivative when we look at this. So if we're talking about when a graph is increasing or decreasing, we're looking at when the second derivative is positive or negative. So if the second derivative is positive, and this is, I'm going to write it a little bit more at the bottom here in a second. If the second derivative is positive, then that means that the first derivative is increasing. That's what we know from section 3.3. When the second derivative is positive, the first derivative is increasing. What we know from the previous slide is that f prime is increasing means that the graph is concave up. So these are just all equivalent language. They sound different, but they're all equivalent to one another. And we can do the same thing on the second line here. We can talk about the second derivative being negative. So if the second derivative is negative, then the first derivative is doing what? Decreasing. And if your derivative is decreasing, then you have a graph that is concave down. So these are all equivalent pieces of information. Now, the reality is that when we test whether or not something's concave up or concave down, we usually sort of ignore the in-between step, kind of ignore the information about the first derivative. We just test, is the second derivative positive? If so, it's concave up. Is the second derivative negative? If so, it's concave down. So we use sort of these outer pieces of information as we're taking a look at that. Now, there's one other thing that we haven't talked about. We've talked about when the second derivative is positive. We talked about when the second derivative is negative. The part we haven't talked about is when the second derivative is actually equal to 0. That is where it changes from positive to negative or vice versa. When that happens, we have something called an inflection point. So all an inflection point is it's the place where a graph changes concavity. That is, it changes from one side of it being concave up to the other side from it being concave down. And we can talk about that, and it could have multiple places where it does that. So let me draw you one graph that you have seen before. And I could keep going with the graph, but what does this more or less look like? A sine or a cosine graph, exactly. This at least has those kind of features. So I'm going to plot in here the places where this would be referencing. An inflection point would be occurring at roughly these spots on this particular graph anyway. And what you're sort of envisioning is that if you take a look at this graph and splitting it up into the places between the green dots, the first piece I've marked in blue is actually concave up. The second piece is concave down. So that dot between them is the place where it changed concavity. And you could keep doing this process on as you go. Now, you don't have to have multiple inflection points. You could just have one, or you could have none. If you were doing a parabola, this parabola is flat out concave down, done. There's no inflection points. So you don't have to have a concavity change. But if you do have a concavity change, it's called an inflection point. So far, so good? All right, let's do an example. We have an example of a function here. This is a pretty simple function for us to start with, on purpose, of course. And we're supposed to determine the intervals where it's concave up, concave down, and we're supposed to identify inflection points. Might want to make note of the fact that this word is points, which means we're looking for an ordered pair here. We will have an XY ordered pair because it says point, not just an inflection number or an inflection value or the X value of the inflection point or something like that. We're actually going to get an ordered pair for that. Okay? All right, concavity is all about which derivative? Second derivative. So we need to find a first and second derivative. So then, what is the first derivative of this particular function? Perfect. Then we need a second derivative, right? So what is the second derivative? 12x squared, I think is what I heard. And then what? Minus 12. Good. All right. What we're about to do now is going to feel a lot like what we did in 3-3. We're going to set this equal to 0. By setting the second derivative equal to 0, what are we actually going to be finding? What happens when the second derivative is equal to 0? Nope. First derivative equal to 0 means we might have maxes or mins. What happens when the second derivative is equal to 0?
Concavity changes.
Concavity changes. And what did we call that place where concavity changes?
Inflection.
An inflection point. So we're actually finding these things out of order. I recognize that, but that's the reality of how we find them. We're going to find the location of the inflection point first. Okay? So finding the inflection point is finding the second derivative equal to 0. And we're going to solve this. So we've got 12x squared equals to 12. So x squared is equal to 1. What is x? Yeah, plus or minus. Good job remembering that piece. We have a plus or minus 1. So we actually have 2 inflection points. So our inflection points, one of them is going to be at 1 something. The other one is going to be at negative 1 something. How do we find the other something? Plug it in where? If we plugged it in the second derivative, we get 0. So the original. We plug it back in the original. The point is a point on the original graph. So we plug the x values that we're working with here, 1 and negative 1, into the original equation. So we're looking at finding f of 1 and f of negative 1. So what happens when we plug negative 1 and positive 1? We'll do it one at a time. Positive 1 into this original equation up here. Positive 1 gives you 0. Okay, good. What's negative 1 give you? It's not 0. What is it, Micaiah? Close. I think you should get a negative 4. Is that right? Okay. All right, so our inflection points are 1, 0, and negative 1, negative 4. Excellent. Okay, so I mean, like, that's half of the question. But how do we then go about finding the concavity? Well, we find the concavity in the same way that we found where the intervals were increasing and decreasing. We do a number line. So we're going to set up a number line, and the reason that we need the number line, or the way we needed the second derivative to the number line, is because on the number line, we're going to put those places where we have inflection points. So the negative 1 and the 1 go along the number line. Because if those are the places where the concavity changes, then between them are the places where we can talk about the concavity being either up or down. So we need to test some points. Tell me a point you'd like to test before negative 1. Negative 2. Between negative 1 and 1? 0, he's our friend. And then after 1? 2. Okay, so now here comes the question again. In which function do we test them? Original, first derivative, second derivative. It's the second derivative, yeah. Because the second derivative is what tells us whether something is concave up or concave down. So we're going to test each one of these points into the second derivative. And the reality is we don't care what the number is that comes out. What do we care about? Whether it's positive or negative. So plug in negative 2 into the second derivative, which was most cleanly written right here in green. What happens when you plug in negative 2? You end up getting a positive. You actually get, what is it? Like the number 36, I think. What happens when you plug in the number 0? You get a negative. And what happens when you plug in the number 2? It's positive. Yeah, it's positive again, right? Alrighty then, so what we have to figure out then is what that means. When the second derivative is positive, what does that mean? What does it mean for the second derivative to be positive? It's concave up. And if the second derivative is negative, then it is concave down. So this one, visually, it looks something like this. This graph is concave up here, and it's concave down between. Now, let me write out the solution then before I do that, and then I'm going to have you look at your calculator. So it asked us where it was about the concavity. So it's concave up on negative infinity to negative 1, union 1 to infinity. You have to write it in terms of an interval, just like when we were doing increasing, decreasing. Move this up a little bit. And then it's concave down between that. That is from negative 1 to 1. So this piece of information, along with the other boxed-in inflection point and piece of information, answers the question. Take your calculator. I'd like for you to graph it. Go ahead and put in the original equation, x to the 4th minus 6x squared plus 2x plus 3. And I'd like for you to double check to make sure that it has this sort of a view when you look at it. So it should look something like this. I'll draw it in green up here. Just a standard negative 10 to 10 window, I think, works on this one. Did you get it, Jamie? Does it have that basic picture, basic view? Yeah. So you should be able to verify with your calculator when you're done that what you just said makes sense. Put in the original equation. X to the 4th minus 6x squared plus 2x plus 3. And it should look like this piece up here in green. More or less. I don't promise it, but it looks something like a W. All right, you guys ready to see what else we can do with the second derivative? There's something else interesting that relates back to section 3.3 that we can do with the second derivative. And we do this with something called the second derivative test. The second derivative test allows us to decide if a point has a maximum or a minimum. Now, we already have other methods to do that, no doubt. But, I mean, how many methods do you have to add two numbers together or subtract numbers? You have lots of ways to do them. You may not know all of the ways to do them because you haven't explored the ideas, but there's lots of ways to do different things. So this is simply another way of deciding if a function has a maximum or minimum. And it's based on the second derivative. So if you have a point where you have a critical point that's got a derivative equal to 0. Okay, so we're not concerned, we can't do this, or it doesn't apply, I guess you could say, for where the derivatives are non-existent. Right? We do critical points finding out where they're equal to 0 or where the derivatives are equal to does not exist. So this doesn't work for the does not exist case. It only works for when derivatives are equal to 0. So when we find where the derivative is equal to 0, we called that a critical point. We did that in 3.3. The next thing we did in 3.3 is we set up a number line, right? And we split our number line into intervals and we did some test points. And that's all well and good. But the other way that you could do it is you could use those critical points and you could actually plug them into the second derivative to test whether they're a maximum or minimum. So think with me for a moment. The first piece here says that if the second derivative is less than 0, something happens. What does it mean when a second derivative is negative? Concave down. Very good. So this description right here is the description for where something is concave down. And visually, concave down looks something like that, right? That picture that I just drew, does it have a maximum or a minimum on it? It's a maximum. So if I've got a graph that's concave down and it has a slope of 0, it would have to be having a slope of 0 at a maximum point. And I could do the same thing to talk about this below. So this one right here talks about a graph that has a second derivative that is greater than 0, which makes it concave up. And if a graph is concave up, it looks something like this, and a slope of 0 would be at this particular point, which is a minimum. And these are all relative extreme points, too, so they're local maxes, local mins, relative max, relative mins. Okay? If the second derivative doesn't exist, you just can't use this information. This test won't work. Okay? So let's give it a shot on one of them. We're going to do another function. This is one of the places where your notes, depending on when you print it off, may be wrong. I need that to be a plus sign between them. So if yours has a negative sign right now, just change it to a plus. That's the one we're going to work with, okay? So we have a function that's x squared plus 1 over x. And we're asked to find the critical numbers, which we've done, and we've been doing now for a couple days. And then we're going to use a second derivative test to decide if they're a max or a min. That part's the new part. So how do we find critical numbers? You take a first derivative, and you set it equal to 0. Or, and truly, we'd also set it equal to does not exist, except that then we couldn't use the second derivative test. So we're only concerning ourselves with the equal 0 parts on this. So we want the second derivative to be equal to 0. I didn't mean second. I said that wrong. I'm sorry. We want the derivative to be equal to 0. How are we going to find a derivative of this function? Quotient rule is one option. You could do a product and a chain. That's another option. There's a third option that's easier than the ones you've described. How about we do this? I haven't found any derivatives yet, but I will argue with you that that value right here is much easier to find a derivative of than using product or chain rules or quotient rules with the first one, right? They're going to give you the same information, so if you choose to use a different method, that's fine. But this one does actually simplify really nicely with some algebra. And the reason it does is because the denominator only has a plain simple x in it. It doesn't have any addition and subtraction in the denominator, so it's kind of nice. So I'm going to go with this last function that I've sort of reduced this into and find my derivative that way. What is the derivative of x plus x to the negative 1? Negatives, right? Negative squared, yeah, the negative 2. So this is 1, and then the exponent of negative 1 comes down in front. We have a new exponent of negative 2. And we're wanting to set this equal to 0. So let's rewrite this with the exponent positive, so it would look like this. We've got a couple options here. One option is that you could find a common denominator and then take your numerator and factor. I mean, that's one option. The other option looks a lot like something we did last time, where you can actually move this to the other side, like so, and you could cross multiply. So we actually would get x squared equals 1. So x is equal to what? Plus or minus 1. So we actually have two critical points, right? So we're going to actually be testing both 1 and negative 1 into this function. But we're supposed to use the what test? The second derivative test, and yet I have yet to find a second derivative, so that would be the next thing I need to do. So we have a first derivative up there. So if we look back at it in terms of a negative exponent up here, what would the second derivative of that be? Okay, so we would end up with a positive 2, right? And then we would have x to the, what did you say? Negative third. Very good. And again, we can rewrite this as 2 over x cubed in terms of plugging numbers in. It might be a little bit more intuitive to think about it that way. So the second derivative test says I can take my critical point, 1 or negative 1, and plug it into the second derivative. So that's what I'm going to do. I'm going to do the second derivative at negative 1 and the second derivative at positive 1. So this would be 2 over negative 1 squared, and then it would be 2 over 1, not 1 squared, 1 cubed. And then 2 over 1 cubed. All right, so what is 2 over negative 1 squared? Negative 2, and what part of that's important? The negative, the sign. So this is negative, and the second one is positive. What does a negative second derivative mean? Concave down, which means this point is a maximum. What does a positive second derivative mean? Concave up, which means this point is a minimum. Now, this says use to determine the local extrema, critical numbers. Do you see that up there at the top, numbers? So we don't actually have to find the y-coordinates for these. It didn't say critical points. It actually said critical numbers. So we can actually talk about it the same way we did in the last section when that phrase was used. We have a local max at x equal -1, and we have a local min at x equal to +1. I don't know that it's any easier or really any more difficult than doing the test points and using the first derivative. It's just different. It's just another way that we could actually find the same information. If the derivative is really easy to find, it's really nice. And this derivative was really easy to find. If the derivative were really complicated, this probably wouldn't be the route that I would go if I were given an option, right? I would probably use test points. If you had a whole bunch of points, even if you don't, you always have to have one more test point than you have critical numbers, which means that if you use the first derivative test, you have, in this case, you would actually have 3 points that you would be testing because you have 2 critical points. So the first derivative test would mean you have to test 3 things. Here I only have to test 2. So there's give and take. There's not really a better option. It's just a different option. All right, we're going to use the same information to do something a little bit different now. This direction said that we're going to determine all significant features, which I think is a funny word, funny phrase, significant features, by hand and then sketch a graph. So let's kind of talk through what significant features might mean in general about a graph. What kind of things on a graph would you consider significant if you were trying to graph it? Maximums and minimums, inflection points. What else might be important to know? If you had any asymptotes, vertical or horizontal asymptotes would be really helpful. This one doesn't have any, but yes, for sure. Not normally, but there are functions where asymptotes are really important. There's one other feature that's often helpful.
Whether or not it's positive or negative?
What's positive or negative?
The x value?
Okay, so we're talking about some x values. How about where the x values are 0? It might be really helpful to know where we have x-intercepts, like where it actually crosses the x-axis, because then we would know whether we have a positive or negative on either side. So if we can find places where it crosses the x-axis with some other points plotted in there, we'll have the ability to be able to see where we have x values that are positive, negative, y values that are positive and negative, and so forth. Okay, so all of those pieces of information are things that we might need to find. Now, this one doesn't have any asymptotes, but it does have a lot of the other features you mentioned. So we're going to look at finding the x and y intercepts. We'll look at finding the maxes and mins. We'll look at finding inflection points. And that might be about all that we need. There's something else that's a little bit interesting going on with this particular function, sine plus cosine. Let's just talk about sine itself by itself. The problem is if you're asked to find or to graph sine, you can't just draw arrows on the end of things and say it goes on forever like a parabola that moves upward, right? What happens with a sine graph? What happens to the graph of sine?
It stays between 1 and -1.
It stays between 1 and -1. What happens to, if it's going to have to be trapped between 1 and -1, what's going to happen between 1 and -1? Think about the picture. What does it do? Yeah, I mean, it keeps repeating itself, right? It's a wave, like in the stadiums, right? You've got a wave going on. It keeps going up and down and up and down. You called it cyclic when you first learned about it in trig. It's called a cyclic function because it repeats itself. And so it repeats itself. Do you remember what they called the space in which it stops repeating itself and where it starts again? What's that? Yeah, what that interval is called. Do you remember what the name is they gave of that interval? They called it a period. The period of the function. Do you remember that word? How often it takes, how long it takes before it repeats itself. So it's a period, like a period of time. So if you take a period of time or an interval of time, do you remember what is the period of a sine or a cosine graph? 2 pi, good. I'm going to tell Dr. Tucker that her students did so well. Yes, you guys remember that piece. That's good. All right, so we have a period of 2 pi. Excellent. So we're going to do some more evaluation. We'll see exactly what we remember from trig here in a moment. The period of 2 pi. Well, sine has a period of 2 pi, and so does cosine. When we add them together, we still get a period of 2 pi. The reason I mention this is because that actually allows us to graph just the graph between pi, or 0 and 2 pi, and know that the rest of the graph is just going to repeat itself. Are you guys with me? So we're actually going to look at end points on this one as well, because we're only going to be graphing one period from 0 to 2 pi. Okay? So, I think that max and min was the first one that was mentioned. I think, Brooks, you mentioned that one, so let's find that one first. How do we find a max and a min? First derivatives, excellent. Sines and cosines are fabulous to find derivatives of. So what's the derivative of sine x plus cosine x? Cosine x minus sine x. What do we do next? Set it equal to 0. You guys are on a roll. Set it equal to 0. Now, this is an interesting one. You've seen it happen in a homework already. I think it was in 3.3. You can actually find out where this is equal to 0 then by moving the sign to the other side. And hopefully somewhere back in your mind you remember that unit circle that you learned in trig. And you can think about it to decide where in the world are the sine and the cosine values exactly the same value. Pi over 4 is one of them. There's one more. Between 0 and 2 pi. We're only going to focus between 0 and 2 pi. 5 pi over 4, yes. So we have two locations, potentially at least, that are maximum or minimum values. Okay, so one way to do this then is to set up an interval and so forth. That's what we learned in the last section. In this section we learned about something called the second derivative test, and I'm going to need to find the second derivative in a minute anyway to do the inflection point, so I'm going to use that test this time. So let's find the second derivative. What is the second derivative of cosine minus sine? Or I should say, what is the derivative of cosine minus sine?
Negative sine minus cosine.
Right. Is everybody good with that? All right, so we're going to use that right here with these particular points to find out whether or not these points are maxes or mins. So we're going to evaluate f double prime of pi fourths and f double prime of 5 pi fourths. All right, so to do pi fourths means that I need to plug in the pi over 4 into the second derivative. So this is negative sine of pi fourths minus the cosine of pi fourths. What in the world is the sine of pi fourths? Square root 2 over 2, exactly. And what's the cosine of pi over 4? Square root 2 over 2. So if I have the negatives in front of both pieces, then they're both now negative. So I have negative square root of 2 over 2 minus square root 2 over 2. So this actually ends up, when you add them together, being a full negative square root 2. Now, all that's well and good, but what we really cared about is whether it was positive or negative. And this one's negative. So if the second derivative is negative, it means the graph is concave down, and a graph that's concave down has a maximum. So one of our pieces of information that we're going to graph here in a minute is that we have a maximum at x equals pi fourths. Now, we are going to actually plot a point, so we need to know the y value there. We'll do that in a second. Let's look at what happens at 5 pi over 4. 5 pi over 4 here is negative sine 5 pi over 4 minus the cosine of 5 pi over 4. So what is the sine of 5 pi over 4? It's what? There you go. It's negative square root 2 over 2. We're in the unit circle here. This is what we should be thinking of anyway. And in the unit circle, 5 pi over 4 is down here. So over here, when it's in the left side of the graph, the sine and the cosine value down there in quadrant 3 are actually both negative. So it's negative square root 2 over 2. But then we've got a negative in front of that, right? So I have the negative sine of 5 pi over 4. So a negative times the negative square root of 2 over 2 would actually give me square root 2 over 2. And then, I'm sorry, I preemptively did that. And then cosine of 5 pi over 4 also is a negative square root 2 over 2. times the negative in front of it. So we end up with square root 2 over 2 plus square root 2 over 2, which is a total of square root 2 over 2, or sorry, square root of 2. Again, we don't really care what the number is per se, but that value is then positive. So when the second derivative is positive, what does that tell you? It is concave up, and if the graph is concave up, it has a minimum. So our second here bit of information is that we have a minimum at x equals 5 pi over 4. Now, it's not real helpful because I'm actually going to have to plot a point, which means I need the y value that corresponds to each of these. But we should be able to find that pretty quickly. How do we find the y value when we know an x value? We plug it into the original equation. Now, the original equation is almost the same as the second derivative, isn't it? So if I plug pi over 4 into the original equation, I've got sine of pi over 4 plus cosine of pi over 4. What's the sine of pi over 4? Square root 2 over 2. What's the cosine of pi over 4? Same thing, square root 2 over 2. What happens when I add square root 2 over 2 plus square root 2 over 2? What is it, Tyler?
Square root 2.
It's a square root of 2, you bet. So at this point, it actually matters what the number is I'm getting, so I need to write that down for sure. What happens at 5 pi over 4? What is the function value of 5 pi over 4? Right. Negative square root 2 over 2, and then another negative square root 2 over 2, which gives me a total of negative square root of 2. Square root of 2 is approximately what? Can you tell your calculator tell you? It's about 1.4. So in terms of graphing, that kind of just gives us a visual perspective of what we're going to be shooting for here. I've actually got something to put on a graph now, so I think that's what I'm going to do next. I'm going to come over to the next screen, and I'm going to start with the graph that I'd like to see when I'm done. So I know my graph is supposed to go from 0 to 2 pi. So back in trig, you remembered how we sort of split this into intervals of 4. And I'm going to double split this because everything I'm getting, my values so far have been in terms of fourths. So each of these now are the fourth of the pi. So the first one is, the first green spot is actually pi over 4. And the middle green spot, the third green spot I should say, is actually 5 pi over 4. We actually need to go up and down as well. So here's the number 1, and here's my number 2. That way I've got the ability to plot a point at 1.4 or roughly there. So I'll do my graph in blue. The first point, 1.4, would be up here. So that's at pi fourths, and then 1.4 roughly. And then I have to be at 5 pi fourths and negative 1.4, roughly there. That's my maximum and my minimum point. How are we doing? It's a lot of work to do these sketches, okay? The other points everything else is going to come a lot easier than the max and the min did because it's a lot of the same stuff. Let's do the inflection point next because we already found the second derivative. How do we find an inflection point when we have a second derivative? Right. We're going to take this second derivative that we found and we're going to set it equal to 0. So if I set that equal to 0, that actually means that I have the sine equal to the negative sign equal to the cosine value. That is, the values have to be the same, but the signs have to be different. So sine and cosine have to have the same numerical value, but one has to be positive, the other has to be negative. So thinking about my unit circle back up here in the top corner, where do I have values on my unit circle where sine and cosine are the same, but opposite signs? Do you remember? What was it? 3 pi over 4 is one of them, and 7 pi over 4 is the other one. Very good. So again, that's why I marked all those pi over 4s, just because I needed some more of them. This will be at 3 pi over 4 and 7 pi over 4. And this is half of an inflection point, so I can evaluate each of these in my original function. So I'm going to find f of 3 pi over 4 and f of 7 pi over 4. But take a look up at that function. What happens at 3 pi over 4? Well, I've got sine of 3 pi over 4, which is, it's a square root 2 over 2, and it's positive because it's sine. And then the cosine of 3 pi over 4 is negative square root 2 over 2. So I've got one of them that's positive square root 2 over 2, the other one that's negative square root 2 over 2. So when they add together, we get 0. And the same thing's going to happen at 7 pi over 4, right? Because one of the values is positive and the other value is negative because we're in quadrant 4. So these ordered pairs are actually going to be the same as the x-intercepts, which is why I'm not actually going to have to find a separate piece of information. So this takes care of x-intercepts and inflection points. And those points are actually right here and right here now. So I have x-intercepts and inflection points happening at 3 pi over 4 and 7 pi over 4. Let me label the pi here in the middle just so that I've got one more labeled. All right, the last thing that we're going to find is going to be the endpoints, because one of the endpoints is going to be the y-intercept anyway, so that takes care of both of those at the same time. I'm going to find the value of the point at 0 and at 2 pi. So I need to find f of 0 and f of 2 pi into the original function. So sine x plus cosine x. So what is the sine of 0? It's 0. What's the cosine of 0? It's 1. So when I have 0 plus 1 here, I get the number 1. So this is the ordered pair 0, 1, and I can plot that point right here. And the same thing's actually going to happen at 2 pi, because 2 pi and 0 are the exact same location on the unit circle, aren't they? So they have the same sine and cosine values. So sine is still 0, cosine is still 1, so this is still the number 1. So over here, when I plot my point, I'm plotting the point at 2 pi still up here at y equal 1. And then if I connect these, that didn't do a good job there. Something like that. The graph does not turn around at 2 pi, right? It keeps going up for just a little bit further, so we want to draw it so that it does continue to go up from there. But this actually just looks sort of like a taller version of a sine or cosine graph. And it's a little bit off-center, right? Because it doesn't have either an x equals 0, 0 as a point or a peak as a 0, a peak there, a maximum at 0, at x equals 0. But this is what the graph would look like. You can confirm this with your calculator as well, right? Sure. Okay, we've got one last example. It's a pretty quick one. It's got a lot of information in it, but let me talk to you about a little bit of it. They tell us to plot some points here. These are 3 points that we're going to plot. So I'm going to start with those pieces of information. I'm going to plot the point at 0, 0. I'm going to plot a point at negative 1, 1. And I'm going to plot a point at positive 1, 1. And again, depending on when you printed this off, some of these pieces of information as we move through this might look different. The next thing that it tells us is that the derivative is greater than 0. So when the derivative is positive, what does it tell you about the graph? The slope is positive. So what's the original graph doing? Increasing. Very good. So my graph should be increasing before negative 1, and it should be increasing between 0 and 1. So I'm just going to sort of sketch this in here like that for the moment, and we'll actually put some definition to sort of some curving of it in a minute. But I need it to be increasing before negative 1 and increasing between 0 and positive 1. The next piece says that I have a slope or a derivative that's negative, likewise then meaning decreasing. It's decreasing between negative 1 and 0 and after positive 1. So something like this, and I get something that looks sort of like an M. The graph's not really going to look like an M. But if that's all the information I was giving, it could look like that, and that'd be fine. The problem is that I'm actually told some other information. I'm told down here some information about second derivative. It says the second derivative is positive. What does the second derivative being positive mean?
Concave.
It's concave up. And it's concave up before negative 1, between negative 1 and 1, and after negative 1. Like, it's concave up everywhere, except we don't know anything about the points negative 1 and positive 1 themselves. So what in the world is this going to look like? Well, it could look something like this. That's certainly concave up between them, right? That would be concave up before -1. And if you'd like, you can mirror image it to the right-hand side, or not. If you don't want to do a mirror image, you could actually do something like this too, and that'd be okay. So is it concave up everywhere except for 1 and -1? Yes, it is. And it has all those increasing, decreasing features that I originally started with, and the corresponding points that I originally started with. You're going to get to do some more sketches. I think you've got 3 more assigned in this section too. Any questions on this one? All right.